why the medium voltage industry is, I think, almost dominated by the vacuum interruption.
But by 2000, it was more or less complete domination of the vacuum breakers, and there are multiple factors to that.
But recently in the CGRE conference, one of the manufacturer also unveiled 400 kV vacuum interrupter.
So similarly, a vacuum switch or a vacuum breaker at transmission voltages is not new. Technology was there, prototypes were there, working prototypes were there, which work on the field.
Hello everyone and welcome to episode 2 of TPP, the Electrical Drive Power Panel. Now in this episode, we are continuing our discussion with Sandeep sir, Mr. Sandeep Kulkarni, who is coming up with a very rich experience of more than 23 years in the vacuum interruption technology. In the part 1 of this video, we discussed about the history of vacuum interruption and how the vacuum interrupter works. That clear idea we got in the part 1. In part 2, we are going to discuss about why the medium voltage industry is fully dominated by the vacuum interruption technology. And we will also talk about now the vacuum interrupters or the vacuum braking is also entering into the transmission field, into high and extra high voltage market. So we will also discuss on that part. So certainly it's going to be very, very interesting. Make sure you have your pen and paper ready to take all the notes that you will be learning from this video. So definitely go and enjoy this video. And yeah, make sure you subscribe to the channel because there's one more episode of this is coming. And to get that update, you need to subscribe with the bell notification icon turned on. Thank you so much and enjoy the video. Why the medium voltage industry is, I think, almost dominated by the vacuum interruption, and why not the SF6, or rather, what are some of the benefits that we get by using vacuum interruption rather than the SF6 interruption?
Okay, so slightly I'll go back to the history, because when I said that vacuum interrupters started appearing on the scene in the 70s, 80s, or rather I should say vacuum breakers started appearing on the scene, and then they took baby steps towards establishing themselves, and by 90s they were the norm. Vacuum breakers became the norm for medium voltage current interruption. But SF6 breakers and oil breakers still existed in those times, and the share was quite equal. But by 2000, it was a more or less complete domination of the vacuum breakers, and there are multiple factors to that. Let's talk about why oil went into obsolescence as compared to vacuum. So when we say oil, it's a fluid. There are issues related to handling of the oil. Then when the arcing happens, there are byproducts of the oil. It needs to be filtered. Then there are many EHS issues regarding the disposal of oil. Also, the life of the interruption life of an oil circuit breaker is also limited.
Yes.
So there were a number of factors which led to the obsolescence of the oil circuit breakers. So then the two obvious candidates which were left in the fray were SF6 and vacuum circuit breakers. SF6 is, I should say, kind of a workhorse. It has a lot of advantages, and it's a very reliable technology. SF6, as we know, is an electronegative gas. So the most important condition which is required for interruption is that of electronegativity. It takes away all the electrons. It has good thermal conductivity. It has good dielectric strength, almost 3 times that of air at the same pressure. So obviously, it is an ideal candidate for a current interruption. So that's why it existed, and it is still existing in high voltage domains. But again, there are some disadvantages of SF6 as compared to vacuum. The energy required for an SF6 breaker is obviously higher than a vacuum breaker because the stroke is higher. Now, if I correctly mention, for a vacuum breaker of 12 kV rating, the contact stroke is not more than 6 to 8 mm. Whereas if you talk the same for an SF6 breaker, I guess it will be about 30 mm. The contact stroke for the SF6 breaker of the same rating.
So almost
So
3 times.
Almost 3 times. Yes, almost 3 times. So obviously, the mechanism needs to be having more energy to create that much of opening. I think the opening speed is also more required for for SF6 breakers as compared to vacuum. So obviously, the energy content of the mechanism is higher. Then again, SF6 gas itself became a bit of a concern in the mid 90s, started becoming a bit of a concern because in 1996 Kyoto Protocol, it was declared as one of the greenhouse gases. So this meeting happened in Japan. Nowadays, I think we call it the COP meeting. It was called the Kyoto Protocol in 1996, wherein SF6 was identified for the first time as a greenhouse gas. And not just identified, but the global warming potential assigned to SF6 was somewhere between 23,000 to 25,000 times of that of
Huge.
CO2. So it's huge. So obviously, that created a mindset about SF6 being not so environment friendly. And obviously, since there was an alternative available in terms of vacuum breaker, which was serving the purpose, so vacuum breakers gained traction as compared to SF6 breakers. The handling of SF6 gas is also a challenge. There are byproducts generated after arcing, so the disposal of those byproducts is a challenge. The life of vacuum breakers is certainly much more as compared to an SF6 breaker. So that obviously now is definitely an advantage for a utility, which is looking to what we call as the time between two maintenance operations or time
Mhm.
between two replacement requirements. So vacuum breakers obviously gives a much greater life in terms of the number of current interruptions at the same level as compared to an SF6 breakers without requiring any maintenance. So because of these advantages of having a lower stroke a mechanism requiring lower energy, more environment friendly, and one of the most important advantages I would say is the adaptability or the replaceability. If a vacuum interrupter goes bad, say a vacuum loss happens or the contact welds, you rack out a breaker, you replace the vacuum interrupter, you check, you do the preventive maintenance checks or pre-commissioning checks, you rack in a breaker, it's ready. It's not the same in case of SF6 breakers, I suppose. It's much more complicated to replace one pool of SF6 breaker. You need to drain out the gas, and that too in a manner which is environment friendly. You need to take care of the byproducts which would have gathered due to the arcing. Again, fill the SF6 gas, do the pre-commissioning checks, and then again it's ready for the next round of operations. So obviously there are many advantages of the vacuum breaker technology. I might have missed out some things, but these are the main things which come at the top of my mind. Why vacuum breakers are now dominating, and now it's a complete dominance. The oil breakers do not exist. SF6 breakers only like ppm level they would be existing in the medium voltage, and rest is completely dominated by vacuum breakers.
Yeah, yeah, true. And you touched upon a point where the contact difference, there is a huge gap. So
Yeah.
vacuum, when we say a contact difference and the contact difference between the SF6 breaker, it's almost three times difference.
Yes, yes, yes.
So will that also affect the size of the circuit breaker?
Yes, definitely. So as I said, for a 12 kV vacuum breaker, the contact gap is 6 to 8. SF6 maybe 25, 30. I am not sure exact figure, but it's could be of
Both,
that
yeah.
order. But certainly it's a difference, and that results or that translates into the dimensions of the total pole. Yeah,
Hmm.
so obviously the total pool, since it needs a bigger gap, will be bigger in SF6. The mechanism will be bigger. And why 6 to 8 mm is okay for vacuum interrupters or vacuum breakers? It's because of vacuum. So in the last question, I touched upon how vacuum is playing as a role, more of an insulating medium. Okay, so even a gap of 6 to 8 mm can withstand the required impulse voltages, because these gaps are designed from the impulse voltage withstand point of view. So for a 12 kV, the rated impulse withstand voltage is 75 kV. For 36 kV, it is 170 kV. So these gaps are designed, or the gaps are defined or constrained from this impulse voltage withstand performance. And since vacuum being an excellent insulating or dielectric medium, even such a low gap, with such a low gap, it can withstand with impulse voltages as high as say 75 kV for a 6 to 8 mm gap. In fact, 6 to 8 mm gap can withstand even higher than that. But I'm saying 75 kV because it's the rated voltage for 12 kV range. So yes, here the key player is the vacuum as an insulation medium, which is ensuring that we have a low contact gap.
Yeah, correct. I think, and after listening all these advantages, I'm 100% sure why the medium voltage industry is completely dominated by the vacuum. I think that's the best choice that we have, considering the available options that we have. Vacuum
Yes.
is the best choice, and I believe I will not be surprised if vacuum technology soon also dominates the high voltage market. So currently, it is dominated by the SF6 interruption, but recently in the CGRE conference, one of the manufacturer also unveiled a 400 kV vacuum interrupter. So
Mhm.
certainly this vacuum technology is also entering into the high voltage world. So
Yeah.
anything that you would like to talk upon that?
Yeah, certainly. As you rightly said, the vacuum interrupters or vacuum interruption technology is making its foray into the world of transmission class breakers, because these 12 and 36 kV breakers, we call them as a distribution class. 72 kV onwards are the transmission class. Um, and certainly, yes, there is a lot of traction for vacuum breakers to make exposure in the vacuum in the high voltage domain also. I'll go back a bit in history. As I said, the vacuum interrupters were developed somewhere around 60s, 70s, the commercial products. And obviously, 12 kV was developed, 24 was developed, 36 was developed. And we would not be surprised that to know that even 72 kV vacuum interrupter was developed in 1980s itself. Okay, so it was not new. So there are literatures available. There are, in fact, photographs of prototypes available, which inform us that even in the 1980s, 72 kV vacuum interrupter was available. Even before that, I had read in one of the literatures that in 1970s or late 60s, there was a vacuum switch which had a rating of 168 kV or 150 kV. I don't remember the exact rating, and it had 8 interrupters in series. So a vacuum switch operating at transient voltage is not new. It's like electric vehicle is not new. We know there were prototypes or there were examples of electric vehicles or EVs way back in 1930s or 40s. So similarly, a vacuum switch or a vacuum breaker at transmission voltages was is not new. Technology was there, prototypes were there, working prototypes were there, which worked on the field. But those times, the alternatives were much more attractive. SF6 breaker was there. It, like I said, it was a workhorse,
Mm.
reliable, um, and accessible. And that time we did not know about the environmental impacts of SF6. It was able to handle, say, 40 kiloampere, 50 kiloampere. You asked for it and it delivered. So that technology was available, that technology was mature. And that's why in those decades, the vacuum breaker technology at transmission class may not have gained that much traction. And there were some challenges in industrialization of big size vacuum interrupters, because when you say 72 kV or 145 kV or 245 kV vacuum interrupters, they are quite large in size. And one reason is the dielectric strength of vacuum medium does not linearly increase with the gap. So if you
Mhm.
say you can withstand a certain voltage at 6 to 8 x voltage, you will not be able to withstand 2x voltage if you double the gap. It will be slightly less. And the curve becomes quite asymptotic as you go higher in the gap. So when you want to realize higher voltage interrupters, the gaps increase disproportionately. Not only the gap between the two contacts, but there are some internal floating shields. Okay, so between the floating shields also the gap needs to be accordingly adjusted. So and those increase disproportionately with the voltage, and so the size of the vacuum interrupter becomes quite big. And to have a sealed for life device in such a big size, it was challenge in those times. I'm talking about 90s or 2000s. So it was definitely challenging in terms of brazing technology, the size of the furnaces, and it was not economically viable or economically attractive because SF6 breakers were there. So people or utilities may not be ready to pay the premium for a vacuum breaker as they may be ready to pay today because of all these concerns related to SF6
SF6.
being a greenhouse gas. So yes, my point is the technology was there, products were there even in the last century, like 90s, 2000s of the last century. And what has changed now is SF6 being concerned as the greenhouse gas. So there's a big push to reduce the use of SF6 in our products. And that big push means we need to find alternatives to SF6. So there are two paths. One, we find an alternate gas. A lot of research is happening, as you know, on that front also to find an alternate gas. And second alternative is to use vacuum interrupter as the current interruption medium rather than a gas. So since early 2000s, a lot of research is being done. In fact, in Japan, vacuum breakers at 84 kV or maybe even 145 kV were used in the late 90s or 2000 and early 2000s also. And I was part of a SIGRE working group called A327, which looked specifically at this aspect of application of high voltage vacuum circuit breakers. So we looked at different aspects about what are the challenges in manufacturing of the breakers, challenging in the design, challenges with respect to the interaction with the network, because the phenomenon happening inside a vacuum breaker is different what happens inside a SF6 breaker. So even the interaction with the network will be different. So there was a lot of study with respect to that. But in the last decade, I can say, yes, a lot of prototypes, not only prototypes, but applications we can see on the site for definitely 72 kV, but even 145 kV in Europe, Japan, China, USA. There are examples of 145 kV vacuum breakers serving on the site. And as you said in one of the conferences, you saw a paper or a demonstration of a 400 kV. I definitely have seen a 245 kV prototype in the literature. So if definitely if 400 is there, then it's definitely a big news. So this is where vacuum interrupter technology stands today in the field of high voltage breakers, and that's going to be the future. So as I said, either an alternate gas or vacuum interrupters utilized at say 245, 400, 765 looks quite difficult. Maybe we will need to connect multiple interrupters in
Yeah.
series to achieve 765 kV. But we don't know where the technology takes us in the next decade. But it will be an interesting decade to see how the vacuum interrupter technology progresses.
True, true. I think you mentioned now, since till a certain voltage limit, like 52 kV, the ban on SF6 is coming soon. There are already regulations in place. And maybe in coming years, they will also ban the SF6 from transmission products.
Yeah.
That is going to happen. So, and that is also the reason why now all the manufacturers are looking for alternative of SF6. Like you mentioned,
Yes.
vacuum could be one of the potential candidate for that. So that's the end of part 2 of the discussion I had with Sandeep sir. Now we discussed about why the medium voltage industry is fully dominated by the vacuum interruption. Sandeep sir clearly lists down some of the advantages of that. And then we also discussed about the vacuum interruption is now entering into the transmission world. So some of manufacturers, they have already unveiled 400 kV interrupters or 400 kV circuit breaker with the help of vacuum interruption. Of course, there are research is going on, and soon I think we should not be surprised if we see the high voltage or extra high voltage industry is also dominated by the vacuum interruption technology. In the part 3 of the discussion, we will talk about what were the challenges to scale this vacuum interruption to a very high level, because now since ban on SF6 is coming, everybody is trying to shift to vacuum or some other alternatives. But what were the challenges in the past to scale it up to that level? That we will talk, and Sandeep sir will share with us all the details about it. And in the end, Sandeep sir also shares some of the crucial opportunities for young engineers in the vacuum interruption technology. Whether the future of this vacuum interruption is very bright, there are a lot of opportunities, or there are no opportunities. That you will come to know in the end of part 3. That link I'll provide down in the description, and if you haven't subscribed, make sure you subscribe to the channel so that you get all those updates. And again, if you have any questions, feel free to put it in the comment section below. We'll pick some of the interesting questions and we'll try to answer them as well. Thank you so much for watching, guys. I'll see you in the next episode. But till then, keep watching, keep learning.